The Alexander Sells Saga, Chapter 5A, Nigeria, first time round. And this is what I found when I was there. A couple of weeks after my arrival, Richmond Johnson, the head of engineering, returned from leave, and I received my official introduction. When I asked him what was my brief, he replied, "Everything that is corroding is your problem, and everything that will corrode will be your problem." By this time I'd read a lot of the records and correspondence and decided that I could do as good a job as any of the previous corrosion engineers. So I told him I had started to gather information for a report on the corrosion status of the whole region, which would take about 6 weeks to complete. It became clear that the section was drifting badly and falling apart at the seams in the process. One of the technicians, Henderson, was off work sick from the time of my arrival and died a short time later. Mark Erifaka left the company but had set himself up as a contractor, so was still available. The mainstay of the section was a very reliable technician called Dunomwe Ebediak, as seen in the picture, who was better at his job than any engineer I had ever met. There were an assortment of contractors' technicians who worked regularly for the section, and I later managed to get 3 of them onto the permanent staff of the oil company. About 30 local contractors were offering their services, and a number of these turned out to be very good at their jobs. Within a couple of days of taking office, the facilities engineer, Godfrey Igboin, introduced himself and told me that he had to repair 2 swamp flow lines 2 or 3 times since they had been constructed only 6 months previously. He said, "You are the corrosion engineer, stop them corroding." I thought, it was he, you know. I wish I was back in North Wales, blah blah blah. But I said, no problem, give me the drawings and I'll get on with it. I looked at the drawings and discussed the situation with Dunomwe, who told me that 2 pipelines, Ekulama 14 and Ekulama 17, were connected to the cathodic protection system at Ekulama flow station, which was built on a platform in the swamp. These 2 flow lines were coated with a special thin film of epoxy compound that had been applied by the manufacturers NAPCO in the USA. The company had asked for a cutout of the damaged pipe to be sent to them for examination, and I was shown a length of 6-inch diameter steel pipe which was coated with a thin layer of black plastic material. There was a bit of a mystery, as this had been a thin layer of red plastic material when the pipeline was laid 6 months before. The coating had changed colour during 6 months in the swamp water. The leak was through a clean hole in the metal, which looked as if somebody had pressed their thumb into it at the site where the coating had obviously been damaged during the construction of the pipeline. From my experience in chemistry and a bit of imagination, it looked as if the metal had simply dissolved, and from what I had read in Peabody's, metal dissolving in acid could be accelerated by stray current. But where was the current coming from and going to, I wondered. I looked at the drawings and saw that the sites of the leaks were close to the route of the delivery pipeline from Ekulama flow station, and the cathodic protection current from our own ground bed could easily be drawn from these pipelines through the swamp water to a coating fault in the delivery pipeline. We confirmed that in an attempt to ration the cathodic protection current out among the various pipelines in the facilities, resistors had been placed in the flow line circuits and had been adjusted to restrict the amount of current they could draw. He explained that each resistor had been adjusted to achieve 1.45 volts, measuring between the flow line and a half cell. They had been told that 0.85 volts, that's 85 millivolts, was the criterion for achieving cathodic protection. We installed a sacrificial anode at the closest point on these two pipelines to the delivery line and removed all resistors from the flow line circuit. I reasoned that this would allow the stray current to leave the pipeline through the anodes. No further leaks occurred to any pipelines associated with Ekulama flow station during the following 3.5 years that I was on seat. My reasoning had been correct, but I was not to know that, as only time would tell. However, I was fairly confident and reported to Godfrey that we had solved his problem at Ekulama. Good, he said. Now you can go out to Agbada and stop the flow lines leaking outside the flow station. Oh shit, I thought, as I knew the tangled mass of rusty pipes that I would encounter at any land location. Abdullah Bukar was Godfrey's assistant, who took me to the site, which was as bad as I had anticipated. The problem was not what I had expected, and had been the subject of several previous corrosion engineers. Most of the flow lines entered Agbada flow station from the other side of the approach road under which they were buried. This road showed many signs of excavations, and Abdullah told me that leaks were a regular occurrence. He also said that my predecessor had installed sacrificial anodes, but the leaks had continued. We had a good look at the site, and I made thumbnail drawings of the layout showing the positions of the anodes, etc. I took voltage readings which showed that all the pipes under the road were theoretically protected by the sacrificial anodes. Back at the office, I drew a circuit diagram on a copy of the pipeline layout in the area. The position of the ground bed was such that the bare flow lines, which were laid on top of the ground, could readily conduct the cathodic protection current to any coating fault on the delivery pipeline which was buried close to their path. The delivery pipeline was connected to the cathodic protection system across the road close to the flow lines crossing. The reason why the sacrificial anodes had not worked was clearly due to their position. I relocated them in position close to the delivery pipeline and connected all of the flow lines together so that the stray current could pass through the sacrificial anodes without causing damage to the pipe metal. The system worked, and there were no more leaks at this site, but the voltages on some of the flow lines were well below the level recommended to achieve cathodic protection. I was confident that the arrangement was correct, as the problem had been a simple question of electrical discharge. The arrangement constructed by the previous engineers had met the recommended voltage criteria, but the measuring technique was inaccurate. I started to investigate the nature of the voltage readings and organised 30 trial holes to be excavated at locations of particular significance based on the readings in the records. I chose points at which the pipelines had been in position for many years, and records showed that it had either consistently met the criteria or been consistently unprotected. I reasoned that the pipeline should be either in very good condition or very bad conditions. We needed to find coating faults to ensure that the pipe metal had been subject to backfill. We went out with a Pearson survey equipment which seemed to be fairly faulty, but in fact turned out to be perfectly correct. The locations selected had been coated so poorly with bitumen that it had degenerated at each location to a paper-thin covering with so many holes that it looked like black lace. The voltage reading at each of the locations showed nothing to indicate the condition of the pipe metal. Remembering that there was supposed to be corrosion where the pipeline was less than 850 millivolts, that's 0.85 volts, negative to the earth, we noted that this was sometimes the case, but we also found corrosion in areas where the voltage had been over 1.5 volts. Well, we also found no corrosion on pipes that had been buried for over 10 years in a corrosive environment where records had consistently showed readings less than 0.500, that's 500 millivolts. I also found that moving the reference electrode, I could get a variety of readings, some of which would satisfy the most criteria. At Rumwekpe, I recorded readings from 500 millivolts to 2.8 volts without disconnecting the lead from the pipeline. I simply moved the electrode in the direction of the ground bed, which was over 400 metres from the pipeline. Since I had not changed the position of the connection to the pipeline or altered the cathodic protection adjustment, the only thing that changed was on that side of the meter to which the electrode was attached. But I had been assured that the electrode was used as a standard reference potential, and taking this to mean that it did not alter. The books and experts said that the voltage on the meter was the pipeline potential compared to the potential of a standard reference electrode, which had a stable reaction of internationally recognised value. I did not dispute this, but something was clearly wrong with the system. I found that I could go to most locations and achieve the voltage which would satisfy the criterion by simply moving the electrode. The instruments for taking the measurement said that the electrode should be placed over the top of the pipeline, but in some cases there was a ½ metre of cover. Others, there was 3 metres of cover. I also discovered that if the coating was good, the presence of the pipeline made no difference whatsoever to the readings. The voltages seemed vary independently of the pipeline, and I even found that they would fluctuate at some locations. Even when I switched the cathodic protection off, the voltages would vary, but would be at a lower plane. The cathodic protection seemed to shift the electrical potential of the whole pipeline and alter the magnitude of certain earth potentials. I was then able to relate some of the voltages to coating faults and reasoned that there were potential variations in the ground itself due to the cathodic protection current passing from the transformer rectifier to the coating fault. Experiments confirmed that this was the case, and I found that the voltage would reduce to about 250 millivolts if the electrode was placed close to a bare patch of the pipe that was still buried at the bottom of an excavation. However, as soon as the pipe was clear of the soil, the readings would jump to 1.5 volts, or whatever value was at that location remote from the pipeline. There was clearly a voltage gradient that could be plotted and would be of value in coating surveys. At this stage, I had grabbed a young engineer called Ben Iuha, who was with the oil company to fulfill his obligations in the NYSC. This is the National Youth Service Corps, whereby students are expected to serve their country for a year after graduating to pay their debt to society for their education. Ben had been allocated to another engineering section who regarded NYSC personnel as a nuisance to be tolerated. I needed staff as mine seemed to be dying and resigning about my ears, so I was glad to use any passing body. Ben was keen to be in useful occupation and had a curious and intelligent mind. He had completed his education in the UK and learned a small amount about cathodic protection series that is taught to all engineers. I told him that I had some new techniques, and he took a crew of contractors to put them into practice at Bomu Manifold, where there had been a problem which baffled the last 2 corrosion engineers. In spite of building another ground bed, installing a second transformer, they had not been able to improve the readings to meet the criterion for cathodic protection. We knew that Bomu Manifold had been bombed during the Biafran War, and we had the as-built drawings produced for its rehabilitation. I asked Ben to conduct a survey to determine where the cathodic protection current was going to. The instruments that were available at that time were analogue meters based on galvanometers. These are more sensitive when set to the measurement of milliamperes than when set to measure voltage. So Ben was asked to conduct a grid survey of the whole manifold, recording the current variations from a fixed electrode to a roving electrode. I reasoned that the measuring circuit would provide a path through which the different potentials of the Earth could obtain equilibrium when the roving electrode was in contact. He returned with thousands of readings which he had written down on site, and we transferred to their position on a large-scale drawing of the manifold. He was excited that he had detected deviations that indicated some feature was not visible on site and did not appear on the drawings. We plotted these deviations, and the contractor excavated to expose a large valve and some pipe work that no one knew existed. The drawings for this old structure have been destroyed in an office fire, and the rehabilitation of the manifold had been done in a hurry. The as-built drawings had neglected to show that the rehabilitated manifold included some of the old pipework. The remainder of the redundant pipework remained welded to the new manifold and was simply backfilled. The oil flowed and nobody cared except the baffled cathodic protection engineers. We organised the recoating of this pipework and redrew the circuit diagram for cathodic protection. It was then obvious why the previous engineers could not get the voltage readings to meet their requirements. We recoated various other bits and pieces of the buried manifold, and eventually the readings made sense. The problem was solved. During this period, Ben grabbed an NYSC friend of his called Steve Mayaki, who had also finished his education in the UK. He joined our section with enthusiasm, and we looked for an area for him to investigate. It seemed like a good idea to look for stray current corrosion, and we examined the drawings of a few locations for places where the overground pipelines passed close to the ground bed and the buried pipeline routes. These flow lines were on the underside, have been in the ground for years. The underside had been buried with soil eroded and deposited by water flow, wind, rain, etc. Where there were many flow lines on a common trace, the newer ones have been laid on top of the others, which became completely buried at some locations. There were other sites where the traces crossed local paths and had become buried by for the convenience of local traffic. All buried pipelines were connected to the cathodic protection system, and it was likely that the flow lines would discharge current from the ground bed to the earth near the protected pipeline. I asked Steve to take current readings from the flow line to ground at the suspect areas and try to find points of the highest current. We would then get contractors to expose the underside of the suspect pipe for examination for metal loss. Steve returned after his first day of surveying to report that he had not only got the expected readings at one location we'd marked, but that the suspect flow line was actually leaking slightly. He had reported this to the relevant section for repair, and Steve continued the survey over the whole region. Although no more actual leaks were discovered, the metal loss on the flow lines that were discharging current was significant enough to warrant immediate replacement of several sections and proved the practical value of our survey techniques.